I chose this topic because this was close to the heart of C.V. Raman, and today we are celebrating the Science Day. C.V. Raman liked to describe himself or to be described as a co-traveler of light, color and beauty. Light, color and beauty, that's what he wanted to emphasize in that. Of course, he has done a lot of work in acoustics, various other aspects of optics, solid state physics, all that is spectroscopy, all that is history. So what lies at the heart of this? When you talk about light and matter, light interacting with matter, that is what gives you color and other phenomena. So there can be only four things. Ordinary light interacting with ordinary matter, ordinary light interacting with extraordinary matter, and finally extraordinary light interacting with extraordinary matter. What is ordinary light and extraordinary light? Extraordinary light may be a high intense light or structured light. These are examples of extraordinary light. What about extraordinary matter? We all think that we are extraordinary matter. But what I mean here by extraordinary matter is structured matter or matter without structure. We will look at some of the aspects of this. Raman is holding a diamond in this picture. And he, apart from, okay, before we come to the optical part of it and color, let's generalize color. Let us generalize color to our ears. How do our ears detect color? Ears cannot detect color as such, but the musical sounds, that's also frequency of a wave, related to frequency of a wave. So, the so-called acoustic color, the music, and musical instruments. Raman is the first person who did research on Indian musical instruments, especially the vibrations of the mridangam. Mridangam became known internationally only because of Raman's research papers in Nature and other top journals. So he was not only interested in color in the optical sense, but also in various other things. Perhaps he was interested in whatever nature gives and everything. We'll see some of his words of wisdom later. To start with on color per se, I would like to invite all of you to a paradise. How does a speaker invite all the audience to the paradise? If the speech is very boring, the audience can nicely sleep and dream that they have gone to the paradise. But I have a different idea. Let's look at the paradise of phenomena which are related to color. You can read the various phenomena which are there in optics, which we experience, which we do research on, all that. And I have carefully written one word with a different color for an obvious reason, because I am talking about color, so I am using color in a slightly different context. So that's what Raman was fascinated by. Color in nature and color everywhere. So let us ask this question. Is color physical, chemical, biological or political? അക്കിത്തം അടുത്ത കാലത്ത് മരിച്ചുപോയി. അടുത്ത അക്കിത്തത്തിന്റെ ഒരു പ്രധാനപ്പെട്ട വരിയുണ്ട് കളറിനെ പറ്റി. ഓരോ മാതിരി ചായം മുക്കിയ കീറത്തുണിയുടെ വേദാന്തം. രാഷ്ട്രീയ പാർട്ടികളെ കുറിച്ച് അക്കിത്തം എഴുതിയതാണ് 20ാം നൂറ്റാണ്ട് എന്നുള്ളതിൽ. ഓരോ മാതിരി ചായം മുക്കിയ കീറത്തുണിയുടെ വേദാന്തം. അങ്ങനെ പറഞ്ഞുകൊണ്ട് നമുക്ക് കളറിലേക്ക് കടക്കാം. സോ കളറിൽ ഫിസിക്സ് ഉണ്ട്, കെമിസ്ട്രി ഉണ്ട്, ബയോളജി ഉണ്ട്, എല്ലാം ഉണ്ട്. ഈ ലോകത്തിന്റെ നമുക്ക് യൂണിവേഴ്സിറ്റിയുടെ വൈസ് ചാൻസലറുടെ താല്പര്യം കൊണ്ടാണ് ഇതെല്ലാം ഈ പ്രോഗ്രാം നമ്മൾ നടത്തുന്നത്. യൂണിവേഴ്സിന്റെ വൈസ് ചാൻസലർ ഇതെല്ലാം ഉപയോഗിക്കുന്നുണ്ട്, എല്ലാ ഡിപ്പാർട്ട്മെന്റും ഉപയോഗിക്കുന്നുണ്ട്. ഈ യൂണിവേഴ്സിന്റെ വൈസ് ചാൻസലർ ഹൂവർ ഇറ്റ് ഈസ്, ഫിസിക്സ്, കെമിസ്ട്രി, ബയോളജി ഇതെല്ലാം വളരെ ജോയിൻ ടുഗദർ ആയിട്ടുള്ള, വളരെ മെർജ് ചെയ്തിട്ടുള്ള രീതിയിലാണ് ഉപയോഗിക്കുന്നത്. അതിനുള്ള ഉദാഹരണങ്ങൾ പറയാം. കളർ എന്ന് പറയുമ്പോൾ ആദ്യം നമ്മൾ വിചാരിക്കും അത് കെമിക്കലാണ്. ഇറ്റ് മേ ബി കെമിക്കൽ ഓർ ബയോളജിക്കൽ. Biological color, chemical color. But look at this color. I hope you can see it clearly. That color is coming from water. And it doesn't really, it is not related to the chemical property of H2O. Okay? It has all the colors. And chemical, water is often described as colorless, odorless, useless liquid. I mean, so that's the point of it. So, but it gives a color, all the color. That's the physical origin of color. Or if you have a layer of oil on water, you have different kinds of color. And that again, it is not whether it is coconut oil or any other oil which matters. What matters is the physical phenomena related to it. What about biological color? I will come to that shortly. But this is the color which we are talking about to start with, because we are talking about science day. Raman was fascinated by this, the color of the sky, and that is what he triggered his research. Actually, he was on a ship, and he was traveling on a ship. So, what is vacation and what is vocation? Carefully look at the pictures. A scientist goes for a holiday with his wife, and they are enjoying the nice scene in the beach and all that. But the wife is accusing the husband. What is she saying? You are actually thinking of research, aren't you? Because he's thinking of the crystals, color scattering, what happens in the sky and all that. So that is what Raman actually did. This cartoon is not about Raman. But that is what Raman actually did when he was going on a ship. There were two questions for which answers are not known. Why is the sky blue? Why is the ocean blue? So the answer, if I were to write the answer to this question I will say, I don't know the first question why the sky is blue, but I know why the ocean is blue. The sky is reflected in the ocean. So I get 50% mark and pass mark in that examination. So that's our knowledge of color and sky. So Raman discovered the so-called new radiation. We are now celebrating the 28th of February. Can you imagine what actually happened in the last week of February when Raman actually discovered this? They were not celebrating. They were not going around doing something fantastic. They were not giving lectures. They were all washing test tubes and beakers. Why were they washing test tubes and beakers? Krishnan, who was Raman's research student, he observed that some light is coming out of some liquid which he was studying. And then Raman said, okay, there is no chance of any fluorescence here. You know what will give light, it is known. So you didn't wash it properly, go and wash again. Krishnan washed it 10 times and brought back, again some light was coming through from that liquid. So it is not from the vessel. Then they suspected the impurity. Then everybody there, starting from the peon to the director, C.V. Raman himself went and washed the test tube and the glassware. But still, there was radiation coming out of it. Today, okay, this is a day-to-day thing, but why nobody has found it so far and why we don't find it every day? Raman's lab is a very, very special lab. There are 3-4 levels of darkness. Your eye has to get accustomed to it before you enter. You just open one region, there will be a low light region, and next region there will be still low. Finally, it will be a totally dark room, and your eye gets accustomed. Today we have fantastic instruments, very sensitive instruments. We didn't have those days. It's only the eyes which they could have to use. And of course, Raman made some simple setup. So in that kind of acclimatization, you can see the glow coming out of it. So if you wash it 100 times, still the glow is there. Then Raman found it is not from the impurity, it is from the molecule itself. And that is what the famous lecture which he gave, the new radiation. And that is what was going on in the last week of February, that time. I do not plan actually to give a technical talk on Raman effect, Raman spectroscopy and all that, because most people know. And further, the purpose of this lecture is not that, it is more general, because I guess people from different backgrounds are here. So I will not go into the physics of it, except just to say that you give some energy to the system, and the system gives you some other energy, both higher energy quanta and lower energy quanta. So if you give higher energy, if you give some energy, and the system gives you lower energy, some energy is taken up by the system. Similarly, if you give some energy and get more energy from the system, some stored energy from the system is given to you. And that is spectroscopically shown there by the 3 graphs. Frequency omega, plus delta omega and minus delta omega. This is the basic idea of Raman effect. As opposed to the normal scattering, in the normal scattering, there is no delta omega. It is only omega. There is no exchange of energy. But in Raman effect, molecular vibration states give their energy or take energy go to the higher state. If it gives energy, it goes to the lower state. That is the whole simplified, like the earlier PVC, others were mentioning that you have to explain your research in 3 minutes. So if you were to explain Raman effect in 1 minute, that is explanation you can have. Let's look at some nice pictures. This picture is from Cochin University. They have in their website. What you see is you can read what is written there. The basic the acetone. Acetone is the material here in that cuvette there, and there is a green light, green laser coming in, and what you get is a very bright red emission. So green velocity is green wavelength is different from the wavelength of the red light, and that conversion of green into red happens because of the molecular energy transfer. And this is a demonstration of the Raman effect. A very colorful demonstration of the Raman effect because there is no other red color, only from the sample. The original color from the laser is green. So this dramatically shows, and you can also see the original setup, a very simple setup which Raman had made. That was something like 100 rupees setup, very simple setup, but it has grown tremendously now. Today, if you look at it, it's a true noble phenomenon. What is the difference between a noble experiment and any other experiment? Any experiment will have some limited interest, some limited application and all that. But a noble experiment is supposed to continue to have continued interest even after several tens of years at least, maybe 100 years. Then it is a true noble discovery, which flourishes, which continues to, which grows and which continues to go into better and better uses even for humankind. For example, you may wonder why I put a picture of a horse. Cars, horses, this is the Raman today. It's not ordinary Raman anymore. Today the Raman spectroscopy is called cars, horses, cars, cells and all that. Coherent anti-Stokes Raman, that is cars. And horses higher order Raman, that is horses. And stimulated Raman and surface enhanced Raman. These are the, so the point is that that simple experiment which you saw earlier, that has actually developed into a very, very powerful technique. Who uses it? The industrialists use it, the doctors use it. Professor Girija Vallabhan of Cochin University used to say this always. Today if you go to the doctor will ask you for your X-ray. Tomorrow if you go to the doctor, he will ask you for your Raman, so that the doctor can diagnose it very clearly. So it has gone beyond physics or chemistry or material science. Engineers use it as a standard material. And doctors would also start using it. They are not already using it, I don't know. So that is a true noble work. In this, that inspired by this Raman's work and Raman's interest in this phenomena, especially in color. Let us explore further into color. Let's start with an apple. Apple secrets are finally revealed. I hope MBA students are not sitting here. If they will be expecting some great funda about companies and all that, but that is what I want to reveal here. I want to reveal the real secret of apple. Apple appears red because the red color is scattered and the other colors are absorbed. That is the reason, that is the secret of apple. The secret of apple's color. So a lot of things happen. What you see around us are colored differently for different reasons, which go beyond different branches of science. Let's look at some of them more. There is a lot of what I call between the cup and the lip. There is a lot of. If you look at an apple, you are looking at the sunlight or whatever artificial light coming to the apple and then coming to your eyes. So there are a lot of things happening in between, and that is what gives you finally the color of any object. So what is this cup and lip thing which I am talking about? There are a lot of things between us and the source, for example. We have the light source, a lot of things are happening in the atmosphere. So there are a lot of scattering, a lot of absorption, various things happen. And what you get is finally some wavelength of what. And that remaining wavelength is what gets scattered. So it's a very interesting thing for the students to try to design, to try why our eyes are like this. People are very fascinated by some eyes look very nice. Somebody's beauty or beauty is supposed to be in the eyes. Let's see how the eyes are. What the design consideration for the eyes. First, the source. What is the source? Whatever the source emits. If the source emits X-rays and you have to live in that planet, such a planet where the sun is X-ray, then your eyes will have to be X-ray detectors. If the sun were to emit more of radio waves, then your eyes will have to have antenna, not eyes. So the eyes are instruments to detect the available light on a planet. And the available light on a planet depends upon what light is coming out and what light is actually reaching you. That is the cup and the lip which I am talking about. And that is what finally which decides. And very funny thing now is that we are polluting the atmosphere. So you see that there is a layer which will absorb different wavelengths and all that. And the problem now is that the pollutants are becoming more and more in the atmosphere, and the whole spectrum is slowly shifting into that. So our grandchildren will have antennas and not eyes, not beautiful eyes, but like we have, if they want to survive. And what happens to a species? It survives because it changes itself, it adapts, it evolves. So next evolution of human being, if you continue to pollute the atmosphere, is going to be like that, bigger eyes and all that. This was meant for the students, but I don't see many students. Others have already passed through this. Why you should listen to such lectures? Please read it carefully. What are clouds made of? The child is asking. What I want to tell the students is that students here in the university will be of typically something like 20-year-old or that. So within 10 years, definitely they are going to face these problems. So he gives some answer. It is mostly water. Oh, if it is water, why do they float? Then he says there are some gases, something, he is mumbling, something like that. Then the son is telling him, you can read that. Then why the rest of the sky blue? And he says, beats me, I guess we ought to look up. Then the son tells the father, I take it that there is no qualifying exam to become a dad or mom. So that is why students have to listen to these talks and understand. Very, very practical reason, not for getting a good career, a good job or interview and all. That's all secondary. Primarily the interview with, it's like a self-interview, interview with ourselves. So what does color actually mean? Color means wavelength, and that changes a lot. So let's look at the recent celebrity. Let's start with a very colorless object. Not colorless object, not a very beautiful object. And this object is an elephant. And there is a story of, വലിയൊരു ധനികനുണ്ടായിരുന്നു. അങ്ങേർക്ക് എനിക്ക് എല്ലാ ആനകളെ അറിയാം, അല്ലെങ്കിൽ ആനകളെ പറ്റി കൂടുതൽ എനിക്കറിയാം, അങ്ങനെ ഒരു അഹങ്കാരം ഉണ്ടായിരുന്നു. അപ്പോൾ ഒരാന ഇങ്ങനെ നടന്നു പോയപ്പോൾ, തനിക്കറിയോ ഏതാ ആന ഏതാണെന്നറിയോ, മനസ്സിലായോ? അപ്പൊ കേട്ട ആള് പറഞ്ഞു, സെർവന്റ് പറഞ്ഞു, ആ കറുത്ത തടിച്ചതാണ് ആന, മറ്റേത് ആന പാപ്പാനാണ്. അപ്പോ കറുത്ത തടിച്ചതാണ് ആന. നമുക്ക് ആനയെ ഒന്ന് ബ്യൂട്ടിഫൈ ചെയ്യാം, ആനയ്ക്ക് കളർ കൊടുക്കാൻ നോക്കാം. ആനയ്ക്ക് കളർ കൊടുക്കാൻ പറ്റും. ഇത് വളരെ എളുപ്പമാണ് ആനയ്ക്ക് കളർ കൊടുക്കാനായിട്ട്. ഇതൊരു ഇൻഫ്രാറെഡ് പിക്ചറാണ്. ഇത് സെയിം എലിഫന്റിന്റെ ഇൻഫ്രാറെഡ് പിക്ചറാണ് ഈ കാണുന്നത്. This is of interest to physics, but this is primarily of interest to the biologists, the zoologists. What did the zoologists learn from this? This is something like, I think it cannot be more than 10 or 15 years old. So there is something which till 10 years back they did not understand, which they could understand because infrared photography was now possible. And what is it that they understood? The elephants will be always doing this with their ears. And what do we think? They are enjoying our music. But poor creature, they are just standing in the sun for hours together, and high amount of what we call it music. When they shout, we don't feel that is music. When a Yeshudas of elephant sings a song, we don't think. Or a donkey sings a song, we are not appreciating it. So we think this animal will appreciate our singing, our music. And the poor thing is not doing that, not appreciating your music. What is it doing? This picture tells you. This is a color coded. Of course, you cannot see it like this. This is artificially colored. Because infrared you cannot see. So an infrared photo has to be interpreted, not seen. So false color is given. More bluer you can see the temperature, you can read the temperature. Bluer for the low temperature and higher, the red for the high temperature. So it's a temperature graph. False color, it's called false color. This tells you that the ears are used to radiate the heat. So the poor things are suffering, it is trying to live, be alive in the situation, being creatively alive in the situation. That's what it is trying to do, to keep its life. Elephant is a huge instrument, huge factory. We are all very complicated, huge instruments. And we produce a lot of heat. And that heat is to be given out, so that our temperature remains the same. And that is the mechanism, that is one of the mechanisms by which, for which this. And such information can be obtained. I'm now talking about the information. We get different kinds of insight and information when we look through different, like different windows. If I go look through this window, I see something. If I look through that window, I see something different. That is why different branches of beyond color. Before talking about color as such, I'm talking about the extending color to the ultraviolet, to the infrared, and all that. So that is what we get different kinds of information when you look through different windows. This is again another infrared picture, same story. It shows the regions which are colored differently. It's not a new kind of yoga or anything like that. Infrared yoga you can call it, but this is just viewing through the infrared. So this is what you get through if you look at through infrared. What happens if you look through X-rays, and when do you look through X-rays? When you are in trouble, you go to the doctor, and then the doctor says, I want to see your X-ray picture. So if you look through X-rays, you see a totally different picture. So students always compare which film star is more handsome, Mammootty or Mohanlal. If you take their X-ray picture, they are not going to be very different. Maybe one person's hand will be a little bit on one side, but the X-ray picture will be basically the same. That whatever you think are the distinguishing features are not there in the X-rays. So when you look through different wavelengths, you are seeing, you are getting different kinds of inputs and information. That's the basic of spectroscopy, and spectroscopy is the science of color. I will have a few lessons. Depending upon the time, I will give you 1 or 2 or 3 or 4 lessons. We'll quickly go through that because each one is a topic itself. The first lesson is that color depends on size. That looks, okay, when I was very young, very small, I was this big. I was very nice, bright red and all that, white and red and all that. Now that I am of this size, my color is different. But that's not what I am talking about. I am talking about something slightly different. I am talking about this. This kind of paintings are there in Europe, different churches of Europe. And these were made hundreds of years back. And unlike the colors of the wall painting and all that, it doesn't decay. Because this is not chemical color. This is not because of a pigment. This is, okay, how do you get color? How do you make glass first of all? Glass is made by mixing silicates of sodium and potassium. That's how you make glass. So some families found out the secret. If you add little more other things like some semiconductors into it, of what is called quantum confinement. This is called in physics the quantum confinement effect. What you see here is a photograph of a crystalline region. That is a semiconductor, lead sulfide to be precise, and that is embedded by an insulator. When a semiconductor is embedded by an insulator, you have a band gap difference. So it is what is called a potential barrier. The electron in the crystal is not able to escape out of the circle because of the band gap difference. That is called quantum confinement. And these objects are called quantum dots. These were made unknowingly. Quantum mechanics was not known when the churches were made. But they had a secret. They knew that if you take it through a particular temperature, you keep it at that temperature for a few hours, then you get this kind of colors. So the reason for that color is that color depends upon size. And that is understood only in this. This is another beautiful picture. This church is now undergoing renovation. You might have seen in newspaper. This is the Notre Dame. And Notre Dame, there is a fire accident there, and it is being renovated. Okay, the church building is fantastic and all that, but what I am focusing now is the window of the church. You see the window of the church there, and all windows, several windows through. It's a big, huge hall, and all the windows have such structures. And all that color is permanent color. It stays for hundreds of years. And that is because of using semiconductor particles of different size, semiconductor nanoparticles, quantum dots of different size. So this is an example, a standing example of color depending upon the size. Raman was interested in gels and all that. So this kind of intrusions, what you are saying is nano intrusion of some material in the rocks and all, whatever forms. This is not even rock, this is some natural formation. And that color is due to nano intrusion of quantum dot like island structures in that. So nature hides a lot of beauties and secret from us. So that is why, that was my first lesson. Okay, little more. This is an old Hindi film song. I don't know whether you heard it. Na chahun sona chandi. A young lover is telling his girlfriend, I don't want gold and silver and all that. So, but nowadays girls have to be very careful. If somebody comes and sings to you, Na chahun sona chandi, and you believe him and go ahead with the wedding plans, what happens, you know? I said, Na chahun sona chandi. I am not asking for gold and silver. Bring platinum. That will be what he said. So you have to ask, if somebody sings this song, you have to ask him, what is your idea? Okay, gold, platinum, all these are metals. And the color of metals is another interesting, fascinating story. The color of metals is due to what physicists call a quasi-particle. It's a plasmon. Plasmon is a quantum of how the electrons oscillate against the lattice. That is a little bit advanced physics, so I won't talk more about it. But the color, the reason for color here in metals is what is called plasmonic effects, transitions and all that. And plasmonics is a very useful branch. It's being used for various things, including diagnostic, biomedical imaging and all that. The second lesson is that color does not, not only on size, color depends on structure. How can color depend upon structure? If you ask anybody what is the most beautiful object in the world, the answer will be what I see in the mirror every day. That's the most beautiful object in the world. Okay, fine. What is the next most beautiful object in the world? People will say Mona Lisa picture is the most beautiful object in the world. People have been doing research, scientists have been doing research on this. What is the secret of what is the secret Da Vinci code? What has Da Vinci done to it? How did he manage to get this wonderful color? Even now, after all these years, researchers are publishing papers on the color of, the beauty, the secrets of beauty of this picture. So let's look at some of the results. A lot of research work is going on that. They look at they study the scattering properties, fluorescence and all that without spoiling the picture. And what they found is, it is because the artist used layers, different layers of different materials. Alternate layers of different materials is what he used. So structure. Now I'm telling, right now we are looking at the lesson 2, which says color can come from structure. So this structure where the alternate layers are given, and that is what which gives rise to this color. And this is not only Leonardo da Vinci who has used it, nature uses it. The color you see is a combination of physical, chemical, biological, all effects. Let's look at, okay, you know about what may be the biological or chemical effect. Let's talk about the physical effect in this. These are structured, these materials are structured, and the color is because of the structure. This is structure at all levels, millimeter level, centimeter level, millimeter level, micrometer level, nanometer level, all levels, structure at all levels. And these structures diffract, and there is an interference. All put together it is called iridescence. That is the reason for this color. More on it in this. Butterfly wings. Butterflies were there. Jungle mein more nacha, koi ne na dekha. There is one famous old Hindi film song which says that. That is, peacocks were dancing for all these years, all these centuries. So were butterflies. So were human beings. But we understood this only something like 30 years back. The reason for the color, even now I don't know whether we have fully understood it, is structure. So now we are talking about how color can depend on the structure. Let's look at it more closely. People look through the appropriate microscopes, electron microscopes. What you see is a butterfly's wing, and all of you will agree that it is a beautiful object that you are looking at. Now that is a zoom. Zoom, that point is a zoom, and it is zoomed, and when you look through the appropriate microscope, you see that. And then you zoom one part of it, and you see this. And you take, these are real pictures from research people have done, and given the reference for this particular picture. And what you finally get is that. And all of us will agree that that looks ugly. So what all of us agreed 1 second back that looked beautiful, now we are all saying that it looks ugly. It is the same thing. It's only how you look at it. It's the same butterfly, same wing. Not even the other wing. Okay, one wing may be beautiful, the other wing may be ugly. So, what is the secret of this color? This is structure. This is happening, light is reflected from different part of the structure. So it looks beauty is not skin deep. There is beauty is in the eyes of the beholder. That is what the poet says. And what do the scientists say? Beauty is in the eyepiece of the microscope you are looking at. That is what we have proved just now. So color has a lot to do with structure, how the material is structured. And many of the wonderful colors which you see is due to wonderful effect of the structure of that. Now let me say color depends on intensity of light. How is it? If I shine a little light, more light, will the color change? If you switch on all the lights, will the color of my shirt change? So that's the different effect which we are talking about. And this is where the non-linearity comes in. Non-linear, the world is non-linear. If you want examples of non-linear objects, we are non-linear. Why am I saying we are non-linear? If you were to plot the height of a human being as a function of the age, height on the y-axis, age on the x-axis, then you don't get a straight line. That is why I say we are non-linear. We grow a lot in the first few days and first few months, but we don't proportionally grow. Otherwise, a 60-year-old man will be touching the roof. In fact, we grow, after 60 and all that, we grow down, our size actually decreases. So, things are not. The world is non-linear actually. The world is not linear. Even simple things like even a common man has to deal with, not the physicist or mathematician. What is the price of one banana? Let's say 2 rupees, let's say. Then what will be the price of 1 dozen bananas? Will you buy for 12 into 2? I was trying to do that when I was setting up a house and starting buying things and all that. I used to, 2 rupees. Then I want 12 bananas and 24 rupees. Then the shopkeeper was a very nice person. He gives back 4 rupees. If you buy 1 dozen, you don't have to give 24 rupees. If you buy 1, you have to give 2 rupees. But if you buy 12, he said non-linear. Actually, I took this example I saw in a textbook, NCR textbook of some mathematics class. What is it called? Linear. What they say is that for 1 rupee, this is a 1 pen costs 10 rupee. What is the price of 10? Then there is a star there, and it says, don't think that it is applicable everywhere in life. Things are not linear. This is what is called by non-linearity. Now let's talk about not only physics, other things also. Any stimulus and a response. You give a stimulus to a system, there is a response. You measure the response and the stimulus. To give a clear idea, we can talk about a spring. You have a spring and you add more and more weight to it. So the spring gets elongated. So there is a length, delta L. And this length, increase in length, you plot as a function of, you define a strain and plot it as a function of the stress. And what you get is not linear. So it happens in various physical phenomena, almost all phenomena of interest in, even including biology. So if you were to plot the stress as a function of strain as a function of stress, you will not get a straight line. You may get a straight line to some value of stress. After that, the story is very different. This is what happens in real life also. If you have a little bit stress, little more stress, your health goes down little and little. But if you have too much stress, it doesn't go linearly. It goes non-linearly. If it crosses a little, what I have plotted here is not stress and strain, but the electric field and electric polarization. That is where nonlinear optics come into picture. This is the story of linear. What I have written there is a linear equation, but there is a nonlinear equation. Actually, there is something more to be added to this, and that's something which is getting added to it gives you color depending upon intensity. And what is going to be added to it is an intensity dependent term. And if you have a higher intensity, you have a color change. For example, if you have 2 wavelengths, yellow and green, and give it an appropriate material, if you give sufficient intensity, if you have lasers, what you get will be not only yellow and green, but also infrared and ultraviolet. So color depends upon this kind of effects. This what I am just mentioning in 2-3 minutes is a class of phenomena which are called nonlinear optics. Music, it is well known. I hope some of you have some knowledge of music. Music, it is well known. Harmonics. Harmonics is the one which makes music beautiful. If there is no harmony, it will be cacophony. It will be just random noise. So sa, there is a first sa, second sa and all that. Those who learn music will know the difference. But in optics what happens is, you have if you have a high intensity source, then color mixing can happen, and the colors which you get, the output color will be different from the input color. So color can indeed depend upon that. And nonlinear optics is even more interesting. Today, if you want to buy the best laser available in the market, that makes use of lot of nonlinear wave mixing. This is called wave mixing and all that. This is the first experiment in color, this kind of color change with intensity. What you see is there you have a ruby laser which gives you the red color, and you pass it through a medium, and when you pass it through a medium, you get half the color, that is half the wavelength also, which is nearly violet. This again is shown in an experiment here, actual experiment. That setup, the big blocks are only filters. The big, what you call tanks are only filters to filter off the color so that you see the proper color. So instead of 694, which is red, what you see is 347, which is blue. And color change because of the intensity. High intensity only it happens, this change happens. At low intensity, it does not happen. So that is an example of how color changes with intensity. And this also has another ramification. This is not of importance in spectroscopy. How does a transition happen? How can you go from one energy level to the other energy level? Suppose the difference E2 minus E1 is equal to h nu. This much everybody knows, whichever is your subject. You have to have E2 minus E1 as h nu. But suppose you don't have it. പണ്ടൊക്കെ കേരളത്തിൽ ഹാഫ് ചായ എന്നൊരു പരിപാടി ഉണ്ടായിരുന്നു. ഒരു ചായ വേണം തോന്നാണ്, പക്ഷെ നമ്മുടെ ചായക്കുള്ള പൈസ ഇല്ലെങ്കിൽ ഹാഫ് ചായ മേടിക്കാൻ പറ്റും. പക്ഷെ ക്വാണ്ടം മെക്കാനിക്സിൽ ഹാഫ് ചായയുടെ പരിപാടിയില്ല. Quantum mechanics, it has to be E2 minus E1 equal to h nu. So I cannot say I have only nu by 2, h nu by 2. No, that is not possible. So you cannot make the transition. So what do scientists do when they are in trouble? You have to make a transition. I don't know how to make a transition. I go to classical music. And then what happens? This is linear optics with a low intensity. Now I have nonlinear optics with high intensity, where two photons can take part, two half quantums can take part together, and I can make the transition possible. So this kind of wonderful things happen when the intensity is large. More about it, if you want to study more about it, you can look at this book. The last lesson, color depends upon lack of structure. I told you the second lesson was color depends upon structure. Now I am going to tell you that color depends upon lack of structure. Scientists found out this object, this beetle. It's a beetle kind of. So this again a connection between the different branches of science. The beetle may be of interest to the zoologist for whatever reason, or the environmentalist for whatever reason. But for the scientists, the reason is that gave a very bright white color. So what is the secret of that color? When people looked at it, they found that it consists of a randomly arranged array of nanowires. That's what they found. So lack of structure. It doesn't have, the color changes because there is a lack of structure. There is no structure. So life, let's look at what is a random environment. You know, this is a maze, and it is really amazing because if you go, you will lose your way. You don't know how to come out of it. If you get into it, you don't know where the next one will take you. Where the next turn going to take you. This is a random path. Unlike the roads where it's written, okay, so many kilometers to reach Kanyakumari, you can go through that. But unlike here, suppose you don't know where it will take you next. So this is what is called life in a random environment. And when you say life in a random environment, you may say life is already random because we don't know what will happen in future. So that is actually a piece of wisdom which we have. Okay, now you know what is life in a random environment. Let us go to what is light in a random environment. What is random environment here? Suppose you put light scatterers. You put it randomly. Then light goes and hits and light doesn't know where to go. That kind of random, that is called a random structure. And different kinds of phenomena can occur in a random medium. Why are we interested in random medium? Because we are random media. What do I mean by we are random media? You see how light propagates through our body. Depending upon the wavelength. Some of the wavelengths do not pass through, but some of the wavelengths pass through. So we are actually basically random medium. Again, a connection between there are very different kinds of sciences. Okay, what is the use of this? I will just talk about one aspect of this because of the today's importance. This idea, how light goes in a random medium, is very important for various reasons, for various devices and for biomedical applications. That is why the interest is there nowadays in this. Or seeing through cloud is a random medium. So it has got applications beyond its physics or nanophotonics as such. And finally, it can give you a Raman laser. I will not talk about the details here, but I will just tell you what you are looking at is the fluorescence curve, fluorescence of zinc sulfide and a beta carotene from crushed leaves, and again, these are the two curves, the black and blue curves. But when you put it in a random medium, what you get is totally different. The third curve, which is not clear in this, but it is clear here. So what is the difference between that emission and this emission? This is the emission of, as I will repeat, emission of zinc sulfide, one. The other one, zinc sulfide is an emitter, photoluminescence material. And the other one is this beta carotene, which is there in some of the plant leaves and all that. And that also is a photoluminescent fluorescence material. But when you put them together in a random medium, what you get is a laser. And this laser happens because of the Raman effect. That story connection is, I will give you the reference, you can read. But finally, this is a Raman laser which you can make using this. So it again brings out the connection between different branches of sciences and a very practically useful new kind of laser itself. If you are interested in that, you can read that. It's too difficult to explain it in a few minutes. So I will just give you the reference, and that will tell you about how a Raman laser is designed. I thought it being Raman Day, I should close with that topic of Raman laser. Recently in our lab, there is some newspaper attraction because of the biocompatible Raman laser which we made. But of course, it is not meant as a laser. It is not a replacement for a laser as the newspaper mentioned. But on the other hand, it is actually a random laser. It is not for a practical application, but it can use for sensing. The importance of that is that it can be used for sensing and all that. This is, I call it a Shiva Raman laser because the student's name is Shiva Shri, Venkata Shiva Shri, and the co-guide's name is Shiva Ramakrishnan. So it should be called Shiva Raman laser. And it's a Raman laser basically. It works on the principle of Raman effect. Okay, I have been telling you a lot of lessons. I told lesson 1, 2, 3, 4 and all that. The next lesson is for the next generation to give me, and the next secret of color is what the younger generation should produce. I will close with Raman's statement. The message of the Science Day, the message of Raman and the spirit of science is this. You have to look behind and beyond. And whatever you see is a challenge to explain any aspect of the vast mystery that surrounds us. That's what Raman said. You see a little, and even this little is enough to elevate the human soul. He is going beyond science and religion. What is the purpose of life? The purpose of life is to find the purpose of life. So, what you should find some passion in life. So, what Raman says is, you look at even a small miracle or a little thing, that itself is it's telling us something. It gives us a message. And what a wonderful world that we have around us. That is the spirit of the Science Day. That is the spirit, that's the advice which C.V. Raman gives us. This picture is of Raman Research Institute in Bangalore. It's a photograph taken in Raman Research Institute in Bangalore. And that little tree which you see there was where Raman's body remains were put. And there's a memory for. This photo was taken several years back. I have not seen recently how the tree is. But that gives us the message of So what is the Raman's message? The blue sky is not the limit. Blue sky is not the limit. That's the message you can take. Thank you.